All right, let me just share a whiteboard with you. So last class, we covered the vibration of atoms. And we covered the multi-scale modeling schema of material science. We have subatomic scale, we have vibrations, then atomic scale, subatomic. Just 1 second to picosecond. Atomic scale, microscale, mesoscale, microscale, continuum scale. All right, we learned the basic knowledge of this part. But if you're more interested in this part, I recommend you to go ahead and take a look at density functional theory, first principle, ab initio, atomic scale. We will cover today in the first class. Then we will start dislocations. Dislocations. Atomic scale, let's define what's atom and the atom models. The atom consists of one nucleus, right? What we have in the nucleus. What's inside the nucleus of an atom?
Proton and neutron.
Proton, neutrons, and at the subshells orbitals we have some electrons. So do you guys know the mass of the nucleus? The total of protons and neutrons. What's the mass? Proton mass plus neutron mass is around 1.6 10 to the minus 27 kilogram. Ismail, do you know the mass of an electron?
As I tend to do 36 hocam.
It is more like 9.11 10 to the minus 31 kilogram. So in terms of atom models, which atom model are you guys familiar with? Which atom model? Kaan?
Yes, hocam.
Which atom model are you familiar with? How about Bohr?
Yeah, I think we use Bohr right now.
Perfect. So let's investigate Bohr atom model and the electronic structure of a model. Bohr. So we already learned electrons. They have both wave-like and particulate-like properties, right? Wave-particle dual shape. Properties. So wave-like characteristic of an electron firstly, the first one is the electrons are in orbitals defined by a probability. So they locate at the orbitals, and in atomic theory or in quantum mechanics, an atomic orbital is just a function of describing the location and wave-like behavior of an electron in an atom. So we have a probability function, and this function can be used to calculate the probability of finding any electron of an atom in any specific region around the atomic nucleus. So they are in orbitals which are defined by a probability. The second one, each subshell or each orbital, let's say, they are at discrete energy levels. So the energy is not continuous, but they are located at discrete energy levels. So let's define some quantum numbers. According to Bohr atom model, we have some quantum numbers. And we have the designation of these quantum numbers. By the way, I'm recording the video, right?
Yes, hocam.
All right, guys. The first quantum number defines the energy level, which is N. N is the energy level. Principal energy level. And we start always with first energy level, second shell, third shell, fourth shell, and the designation goes like K shell. Like the first shell is K shell. The second shell is, second energy level is L shell. It goes M, N, O. Let's say we have an atom, nucleus, and the energy levels are N is equal to 1. Second, N is equal to 2, which is K shell, L shell, N is equal to 3, M shell. So at this specific energy level, we have also suborbital, sublevels, which is, we represent by L. And these are like orbitals. What we said related to orbitals The orbital is a function describing the location and wave behavior of an electron in an atom. And we use this function to find just the probability of any electron to occupy in specific energy scales. So this is first energy level, second, and third. And we have subshells of these energy levels, which are orbitals. Subshells. And these subshells starts with 0, 1, 2, goes till n-1. And the zeroth subshell is S. The first one is P, second one is D, and third one is F. Basically, this L also represents the shape. So this kind of shape. L0 means L0 means we are at the S orbital, which is fair. This is S. L1 is p orbital and shape is something like this. L2 is nothing but, we know it's D. And the shape is like a butterfly. Like the shape of F is very complicated and I can't even draw it. It's beyond my drawing capability. All right, guys, what else do we have? So we know that L is always less or equal to n-1, right? Starts with 0 and goes till L-1. So this is just sublevel. For example, when n is equal to 1, L is just 0, which is S orbital. So we are at the first energy level, which is 1, and here the electron is at S orbital. How about second energy level? Ismail, please help me. What can be the L?
0 and 1.
L could be 0, which is S, or we can go till n-1. L can be 1, which is P. So the second energy level, S orbital, second energy level, P orbital. So this is just sublevel. These are sublevels. And these are principal levels. When n is equal to 3, Ahmet Hakan, can you help me? What can be the sublevels, the orbitals?
Hocam, it could be 0, 1, and 2.
Could be 0, 1, or 2.
And S,
Which
P,
means
D.
S, P, and D. Perfect. Three S, it goes like this, 3P. Three D. Okay, let me just go back. erase this part. We also have a magnetic quantum number, which is denoted by ML. ML. Magnetic. And it starts from minus L and goes till plus L. And the numbers are 1, 3, 5, 7. It goes like this. And it kind of represents the orientation. It represents kind of the orientation. Let's look at some example. When L is equal to 0, we have minus L we start with. So we are defining the ML, which is magnetic quantum number. It also defines the orientation. So here, ML is just 0, right? Because L is 0, we go from minus 0 to 0, which is just 0, and we only have 1 ml. When L is equal to 1, when L is equal to 1, ml is 3, and we go from minus 1 to plus 1. That means P minus 1, 0, and plus 1. And we have just Px, Py, Pz orientations. So ML is always in between the magnetic quantum number plus L to minus L. And let's look at the orientation Px, for example. Px is something like horizontal axis. Py is a vertical axis. Pz is along the z-axis. All right, guys. What else is a quantum number we have? The last one is the spin of electron. The electron can be either spin up or spin down, clockwise or counterclockwise, and we represent them by 1/2 or minus 1/2. So far, so good. So let's solve an example. Let me draw a nucleus here, which has some protons and neutrons. The first shell, it has, let's say, this is ground energy state, so it is 0 electron volt. The second energy level, principal energy level, n is equal to 1. When n is equal to 2, let's say the energy level of this shell is 4 electron volts. Third one, I'm just giving some arbitrary numbers. 6 eV. Let's put another one here. And is equal to 4. Let's say 7 eV. And we have an electron at the first shell. So the energy is increasing as a distance from the nucleus. So let me just draw the energy level. Ground energy state. So electron can only occupy at discrete energy levels. So we are at the first energy level. Okay, Ismail, please tell me what happens if we give this electron to 3 electron volts?
There is no change, hocam. It will remain in the same orbital.
The electron will remain at the ground energy state, right? But
Yes,
what if we give this electron 4 electron volts?
Then it will jump into second one.
It will jump into the second energy level. Right? Perfect. So how can we give energy to the electron? What can be the source?
Any energy type, I think.
Sorry, Ismail, say it again.
Any energy type can be.
Basically, we can do it via light, right? We can send, what is the quantum of light? Khan, what is the quantum of light? What is the subunit that we cannot separate easily?
Is it photon, hocam?
Photon, perfect. We can send some photons to the system. For example, we are sending a photon which has a, suppose we are at this energy scale and 2 electron volts. Then we can jump to this scale, or 6 electron volts. We can directly jump to 6 electron volts. So the question is, what if, suppose we are at the ground energy level and we send the electron 5 electron volts. Kaan, what do you think it will happen?
Can you say again, hocam?
Pardon me, say it again. Say it again, Kaan, I couldn't hear.
Hocam, actually, I didn't understand the question. I said, can you say the question again?
What would happen if we sent this electron, ground state electron, to 5 electron volts? So we are at the ground state and we are sending 5 electron volts to an electron.
It can go second orbital.
So you think it can absorb 4 electron volts
Yes.
and release 1 electron volt and occupy at the second energy level. What do you
Yes.
think, Ismail?
Hocam, I also agree with Tom.
You agree with? Is there anyone who disagrees? It is a good assumption, Khan. Thank you, but it's not correct. Electron can take either all energy or the energy will pass through. Since we don't have any energy state at 5 electron volts, this 5 electron volt just pass through the electron. So it will remain at the ground state, ground energy state. Perfect. So the question is, what happens? For example, we're at this energy state, the third energy state, and the electron releases 2 electron volts. It will go back to first energy state, right? Always the principle is they want to occupy at the lowest energy states. No matter how far you brought the electron, it will tend to go back to the lower energy levels.
May I ask something?
Let me first ask a question. How can we release the energy?
Hocam, when we lower the energy level, energy will release.
No. How can we lower it? How can an electron release energy? Think about this. Maybe we can think about only the photon. The electron can emit photon, right? Emit 2 electron volt photon and lower its energy. Ismail, so sorry, please go ahead and ask your question.
Hocam, in third level, you said that if we release 2 electron volt, it will go down to 4 electron volt state. So what happens if we released 1 electron volt? Is it possible?
So the electrons always, they occupy at discrete energy states. So this electron, if this is the case, cannot emit 1 electron volt photon. In order to go back to the first energy level, it should emit 2 electron volts photon.
Okay, hocam.
So give or take, you can go either upper or lower energy levels. You can go until the ground state. You can go until the first principal energy level. You cannot go down from the ground state. It's like it will be an apocalypse. You can go till ground state, but you cannot go further. Perfect. So far, so good. So please tell me the electron energy states. So let me just reset. Electrons have discrete energy states and they tend to occupy at the lowest available energy state. Let's check the lowest available energy state. So let's say this is energy. First energy state, 1s. This is K shell, right? And n is equal to 1. Let me draw. Sorry. Second energy state, we have S, which is 2s, and 2s. And the spins are spin up and down. Suppose we are filling all the spaces. This is second shell, which is L shell, and n is equal to 2. Okay, what's next?
3s.
What is next? 3s is the lowest of the remaining parts. We have 3s. Electron will occupy 3s first, then
3p.
Okay, we have 3p. Electron will occupy up, down, down. Then
4s.
So you're suggesting that the n shell, when we have 4s, the energy level of 4s is less than 3d, huh?
Yes.
That is correct. So the green one is M shell. Sorry, the yellow one is M shell. And N is equal to 3. But the electron will occupy 4s first, since its energy is less than 3d. Then it will occupy the 3d. Then what's next? We have 4p and 4d, right? N shell. N is equal to 4. Perfect. I think you guys can do all the electron configuration of the given element. For example, I think you can do a magnesium 12. Try to force yourself and check if you have any problem, or aluminum 13, argon 18, or try iron 26, right? Just check if you have any problem with these. Nickel transition metal. Or copper, right? This is another important element, or zinc. All right, so that was the basic reminder of atomic level. Then second class, we will start with these locations. All right, guys. So I'm having 10 minutes break right now, and I'll see you in 10 minutes.